Okay, I have here a string around a washer, and this constitutes a pendulum. You can make a pendulum yourself. Anything with a hole in the middle of it and a circular symmetry, a symmetry about the center, that is something like a ring. And it could be a little larger than this, could be smaller. And we want to make it with thin thread so the thread doesn't have a significant mass compared to the mass that's suspended from the thread. Okay, we call this a pendulum mass, and this is what we call a simple pendulum. The length of the pendulum is measured from the very center of the ring or whatever it is to where I'm holding it. And I hold it between two fingernails, so I'm sure that I have a uniform length, and I am able to measure that accurately and know what the length is. You could also make a pendulum out of a ring for your finger. If you do, just make sure that the stone of the ring is here, so that you at least are symmetric between here and here, so that the center has as much mass above it as below it. Okay, now to count the pendulum, we simply count what I call cycles. Now, everybody calls it cycles. I mean, that's a standard term. Okay, so I release it. 1, 2, 3, 4, 5. Okay, those are cycles. Now, if I count this way, 1, 2, 3, 4, 5, 6, I'm counting half cycles. So that if I counted half cycles for, say, a minute, I could find the number of cycles by dividing the number of half cycles by 2, and then I'd have a count that was accurate to within a half cycle. If you can count that fast, it's not a bad way to count. I can even get really fancy, okay? Now, if I get the rhythm of this thing and decide, okay, we start right here, so start 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, 1 is occurring here, 2 here, 3 here, 4 here. And with that 4 count, if I knew what my actual counts were, so I could count sort of like this. Start 1, 2, 3, 1, 1, 2, 3, 2, 1, 2, 3, 3, 1, 2, 3, 4, 1, 2, 3, 5. Okay, then I know whether I'm on 1, 2, 3, and I know what the last number I counted was, and I can infer how many times the pendulum has swung, and to the nearest quarter cycle, when that minute, how many cycles the pendulum has gone through by the time the minute ends. Now, I need to have somebody out there telling me when to start, when to stop that minute, and we can get ridiculous with that. We can count 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 3, 4, 3, 4, 5, 6. I can't do it. Too fast. Out here, I could probably do 8. Maybe you can. Okay. Now, the idea then is that we're going to measure the length of the pendulum, and we're going to count for a minute. By frequency, I mean how many times, how many cycles there are in a given time interval. So if the time interval is a minute, then the frequency would be how many cycles per minute. So we count the pendulum for a minute, and we get the frequency. We measure the pendulum, and now we have a length and a frequency giving us a point on the graph. Okay, we do that for a number of different lengths. And we get a graph of frequency versus length. Now, the longer the pendulum is, the less the frequency, and it turns out that your frequency versus length data might look something like this. Okay? That could be a frequency versus length curve. Now, probably not. Actually, looking at the shape of this thing, I don't think I have the frequency versus length shape right, but if this is it, then we have this kind of a graph for frequency versus length. And then we can sketch a curve that fits the graph, that fits the trend of the graph, and we can analyze that curve using the methods that we've used for power functions. First, we can see if it is a power function using the test of a constant y factor whenever x doubles. Do we have a constant y factor here? Is this really a good representation of what happens with frequency versus length? We don't know yet. Okay, we don't have actual data, but you could do this sort of thing. You could make this sort of measurement and do this sort of analysis and determine if it is a power function, and if so, about what is the Y factor. And once you know the Y factor, you can get the power of your power function. So what we want to do is determine the Y factor for the data and determine power P, assuming we have Y equals A x to the P. Now, if we can't determine a Y factor, if the Y factor is not constant when x doubles, then the model is out the window and we're not going to be able to use a power function model. Okay, but having obtained the data, we can determine the Y factor and the power, and remember that the power is the Y factor divided by the log of 2. That'll give us our power P. Now we'll continue this. I do recommend that you make a pendulum and make several determine the frequency for several different lengths as best you can, at least 4, 5, or 6 data points, and see what kind of curve you get. Now we'll go on in the next video.